We are first going to try to answer the question, what is electricity? Electricity is a source of energy. Modern living is so dependent on it that life without electrical power is almost unthinkable. But again, what is electricity? And that's not an easy question. To answer it, we must first think about the building bricks of the whole universe. And that includes you, me, and everything there is, even this pylon. If we get in close to the iron, and then into the iron, we will see that it is built up from molecules. And then we will see that molecules are made up of atoms. An atom is so small that we really can't imagine it. It consists of a sort of central blob which is called the nucleus, with tiny fragments of matter called electrons revolving around it. Different substances have different numbers of electrons revolving around the nucleus. Electrons carry a negative charge of electricity. That central blob, the nucleus, is made up of two sorts of particles. One, protons, which carry a positive charge of electricity. And two, neutrons, which have no electrical charge. Protons and neutrons are of about equal size. They're both a good deal bigger than electrons. In the nucleus, there's the same number of protons as there are electrons in orbit around it. For example, this is the atom of the metal aluminum, and it has 13 electrons orbiting around it. So there are 13 protons in the aluminum nucleus. This means that the negative charges of the electrons are exactly equal to the positive charges in the nucleus, and the whole atom is therefore electrically neutral. The electrons are bound to the nucleus by the force of attraction between the negative and positive charges. But in some substances, the electrons in the outer orbit are not very tightly held, and they can be dislodged fairly easily. An atom which has lost some of its negatively charged electrons is left with a surplus of protons in its nucleus. So the atom is now positively charged. A charged atom is called an ion. When the electrons are discharged, they are called free electrons, and all electrical effects are caused by the movement of these free electrons. You remember the aluminum atom. Aluminum is a substance with easily dislodged electrons, and so is called a conductor. Silver, copper, and aluminum are examples of good conductors, while rubber, paper, and wax are examples of poor conductors. So although it's difficult to say exactly what electricity is, we now know that electrical effects are caused by the movement of the negatively charged electrons. And this is the basis of everything we shall learn about electricity. That electrical effects are caused by the movement of electrons. Now we're talking about one way in which electricity is produced. A conventional submarine, when submerged, is driven by the electrical energy supplied by its batteries. And we all know that batteries are needed for flashlights, for starting cars, and for running portable radios. The use of batteries is very extensive, and so we must get to know something about them. We know that the atoms of matter are normally electrically neutral. The electrons and protons exactly balance. And we also know that a movement of electrons is needed to produce an electrical effect, an electric current. So something has got to get the electrons out of the atoms and has to get them moving. One way of doing this comes under the heading of chemistry, and it is called chemical action. Take a glass jar containing sulfuric acid diluted with distilled water. Now take a plate of the metal zinc and a plate of copper, each connected by a wire to an instrument which measures electric current. Next, dip the plates into the acid, and a current flows in the instrument. We have produced electricity from the chemicals zinc, copper, and sulfuric acid, and we call this arrangement a cell. What happens in the cell is this. The acid, called the electrolyte, reacts with the plates, and in the process it pulls electrons out of the copper atoms, transfers them across the cell to the zinc plate, and deposits them there. So by losing electrons, the copper plate becomes positively charged, and by gaining electrons, the zinc plate becomes negatively charged. This process would go on until there was no room for any more electrons on the zinc, and the process would stop with, as we say, the cell fully charged. We would refer to the wire attached to the copper as the positive terminal, and the wire attached to the zinc as the negative terminal. When we connect the plates to an instrument outside, electrons will rush from the negative terminal to neutralize the positive charge on the positive terminal, causing the instrument to register a current at the same time. There would now be room again on the zinc for some more electrons, and the transfer of electrons inside the cell would begin again. The current would continue to flow through the external circuit. However, within the cell, two things are happening. Bubbles of gas are coming off at the positive plate. Hydrogen gas, in fact. Also, the negative plate is being eaten away. Eventually, it would dissolve completely and the cell would be dead. It can never be recharged. A cell like this which can't be recharged is called a primary cell. In practice, the most common type of primary cell is the flashlight battery or dry cell. The zinc plate is now formed into the case containing the electrolyte. The copper plate is replaced by the central carbon rod, and the electrolyte is a paste of the chemical called ammonium chloride. At the bottom, a tar paper washer makes sure the carbon rod doesn't touch the zinc. And at the top, layers of sawdust, sand, and pitch hold the rod in place and prevent electrolyte leakage. In use, the zinc and the electrolyte are gradually used up until the cell is dead. When we connect several cells together, in a flashlight, say, we call the combined unit a battery. Here's a battery where 3 cells are connected together. Now those were primary cells. They couldn't be recharged. Secondary cells, on the other hand, can be recharged, and are the cells used to make up such things as car batteries. This is a typical one made up of 6 cells linked together. Each cell provides 2 volts, so this is a 12-volt battery. More about volts later. This is how a secondary cell works. We have sulfuric acid and distilled water, still called the electrolyte, but the plates are different. The positive plate is lead peroxide, and the negative plate is lead. As the cell discharges, the acid gets weaker, and both plates change into the chemical lead sulfate. However, on connecting the cell to a source of electricity, it can be recharged, and the electrolyte and plates return to their original composition. Water evaporates from the cell in use, and it occasionally has to be replaced with distilled water. In order to get a worthwhile amount of electricity out of a cell, the plate area needs to be as large as possible, so that plates are made with this in mind. Several plates of each sort are connected together, and the interleaved separators make sure they don't touch. Usually the positive and negative terminals are clearly marked. And sometimes there are caps which can be unscrewed for adding distilled water. A vent in each cap allows any gas produced during discharge to escape. Other designs have different adding water systems. And the most modern batteries never need adding water at all. Now, we need to know when a battery needs recharging. And this is checked with this instrument, a hydrometer. It works like this. When a cell is fully charged, the electrolyte is exactly 1.25 times the weight of the same amount of water. We say it has a specific gravity of 1.25. A hydrometer measures specific gravity. It is shown by the figure on the float where the surface crosses it. Here it is 1.16. That means the cell is discharged and needs recharging. You should test the specific gravity in every cell of the battery, by the way. Looking after a battery is fairly easy. You handle it carefully for a start and you keep it clean, particularly the terminals and connectors. Keep adding distilled water, and don't let it go too long without recharging. In this way, your batteries will give you long and faithful service. And before we leave the subject, we'll talk about an important point. We've so far talked only of electron current, the flow of negative electrons toward the positive terminal. And this is how we shall think of current for the time being. However, later on, when you're dealing with electrical machines, you'll come across the term conventional current, which is thought of as if it was a flow of positive charges toward the negative terminal. You will soon learn to use the terms electron current and conventional current correctly. In the next part, we will learn about magnetism. So far, we have learned what electricity is, and one way in which it is produced. Now, we come to magnetism. Magnetism is important not only because it's the basis of the navigator's most important instrument, the compass, but also because it provides the engineer with the means of producing electric power on a giant scale. A simple definition of magnetism is that it is the power to attract. This magnet attracts, for example, iron or steel objects, and they are referred to as magnetic materials. All magnets are not shaped like this horseshoe magnet. Very common are bar magnets like this one. Surrounding a magnet is the space in which it affects magnetic materials, and this is called the magnetic field, or the field of force. We can demonstrate this magnetic field quite easily. We put a thin piece of glass over the magnet and sprinkle onto the glass some iron filings. It may require a tap, but the iron filings will set themselves into lines forming a definite pattern. We talk of lines of force. Although by this simple trick with iron filings we made the magnetic field visible, the lines of force are really quite invisible. Another striking effect of a magnet is that if we hang it up in such a way that it can rotate, it will always set itself to point in a certain direction, and that direction is toward the north. This property of a magnet is the basis of the magnetic compass, on which all navigation at sea depends. A magnetic compass needle always points the same end to the north. We call that end the north-seeking pole, or just the north pole of the magnet. The other end is, of course, the south-seeking pole or south pole of the magnet. The reason why magnetic needles behave this way is that the Earth itself behaves as if there was a huge magnet at its center, with its end pointing approximately, but not exactly, toward the north and south poles of the Earth. In the same way as the compass needle, a bar magnet has north and south seeking poles, or just north and south poles. All magnets, whatever their shape, have north poles and south poles. Coming back to the magnetic field, we give the lines of force a direction and say that they emerge from the north pole and re-enter at the south pole. Similarly with horseshoe magnets, the lines of force are packed close together near the poles, and the field is very strong between them. All the magnetic strength of the horseshoe magnet seems to be concentrated around the poles. This is true of a bar magnet as well. There seems to be no magnetic force at the center. If we put a piece of magnetic material, say iron, in the magnetic field of a bar magnet, and produce the picture of the magnetic field with iron filings again, we see that the lines of force have concentrated in the iron, and it has itself become a magnet. We say that magnetism has been induced into it, and we call the process induction. An interesting case of this is when the hull of a ship in the builder's yard lying in the Earth's magnetic field has magnetism induced into it. This has to be got rid of by the process called degaussing. When the piece of iron is taken away from the field of the magnet, it loses its induced magnetism. It was only a temporary magnet. More lasting magnets can be made of iron, but they do lose their magnetism rather easily. Steel is used for permanent magnets, and they're very much more powerful than magnets made of iron. Some alloys of steel also make strong permanent magnets, and they come in for a lot of uses in electrical machines and electrical devices. If now we take a bar magnet, its north pole is painted red, and bring another one up to it so that its north pole is to the south pole of the first one, the two magnets attract each other and come together with a snap. Not really very surprising, you might think. But what about when we bring the two magnets together so that the north pole of one is toward the north pole of the other? Well, they'll have nothing to do with each other and drive each other away. The principle is that like poles repel each other and unlike poles attract each other. This is the great law of magnetism. Like poles repel, unlike poles attract. The iron filings demonstration makes this clear. When unlike poles are together, the lines of force join up into one field. It is very strong between the adjacent poles. On the other hand, when like poles are together, the lines of force turn away from each other and almost seem to be pushing each other apart. There is a region without lines of force between the two magnets. And that's all we wish to say about magnetism for the moment. As we progress in our study of electricity, we shall find that these few simple facts about magnetism have a profound influence on how the forces of electricity are harnessed for our needs. Earlier, we have seen that electrical effects are caused by the movement of free electrons, and electric current flow is the most obvious of these electrical effects. For example, in a cell, when the terminals are connected to an outside circuit, free electrons flow from the negative terminal to the positive terminal, and we say that an electron current flows. So electric current is the flow of electrons in a conductor from negative to positive. But you'll remember we sometimes refer to conventional current, which is thought of as flowing the other way. Suppose we have an electron current flowing up a vertical wire and passing through a piece of card. It might seem an odd thing to do, but if we try the iron filings trick, we may be surprised to find that there is a magnetic field around the wire. The lines of force are circles with the wire at the center. And they flow either clockwise or counterclockwise, depending on the direction of flow of current in the wire. Here's how we find out which. You imagine yourself gripping the wire in your left hand. Note that left hand with your thumb pointing in the direction in which the electron current is flowing. Then your fingers will point in the direction of the lines of force. In the case we saw, we said the electron current was flowing up the wire, so using this left-hand rule with the thumb pointing up in the direction of electron current flow, the fingers indicate a clockwise direction for the lines of force. If the current flows down the wire, then the left-hand rule tells us that the lines of force have counterclockwise direction. If you want to draw this field, you need to show in your drawing if the current is flowing into the paper or out of it, toward you. Well, think of a dart. If it's flying directly away from you, you would see the flights looking like a cross. So we show current going into the paper with a cross. On the other hand, if the dart was coming straight at you, you would see its point. So we use a dot to show electron current coming toward us out of the paper. These symbols are called dart notation. Using dart notation and the left-hand rule, we can draw the field around this wire showing the direction of both field and current. Current coming toward and field clockwise. Now let's look at a wire bent around and round to form a coil. When current flows through it, there will obviously be a magnetic field of some sort around the coil. And if we perform the experiment with the iron filings in this case, we discover that the magnetic field produced by a coil is very similar to that produced by a bar magnet. Again, we need to know the direction of the field, and this is found with another left-hand rule. You wrap the fingers of your left hand around the coil, pointing in the direction in which the electron current is flowing. Then your thumb points to the North Pole end of the coil. Three things affect the strength of a magnetic field produced by a coil. First, the more turns there are in the coil, the stronger the field produced. Second, the greater the current flowing, the stronger the field produced. And finally, adding an iron core to the coil concentrates the lines of force into a stronger field. And we now have the device known as an electromagnet. Some of the strongest magnetic fields of all are produced by big electromagnets. Now let's think about a most important idea to do with electric current. When we connect the terminals of a cell to an external circuit, electrons flow as a current. But there has to be a force driving the electron current around the circuit, and it is called the electromotive force, or for short, EMF. It is measured in units called volts. Whenever you find two bodies at a different state of charge, if you connect them, there will be an EMF driving a current between them. Now, it isn't necessary for one object to be negative and the other positive. If we have one body negative and the other still more negative, that is, it has accumulated more free electrons, and we then connect them, there will be an EMF between them to drive electrons from the more negative body to the less negative one. Before the two bodies are connected, we say that there is a potential electron flow between them. We say there is potential difference between them. Potential difference, or PD, is also measured in volts. It becomes the EMF as soon as the bodies are connected by a conductor. If there is no potential difference, there is no EMF and no current flow. But speaking of conductors, you'll remember that good conductors are substances with easily detached electrons, which allow current to pass easily. We say they have low resistance. Good conductors are silver, aluminum, and copper, and also carbon and water. And they, remember, have low resistance to the passage of current. Poor conductors, on the other hand, have high resistance. Substances like these with very high resistance are called insulators. But resistance depends on three other things apart from the nature of the material. First, the length. The longer the conductor, the higher its resistance. A greater EMF would be needed to drive the current through it. Next comes the cross-sectional area. The larger the cross-section, the lower the resistance. It's as if there was more room for the electrons to get through. And finally, there's the temperature. The hotter the material of the conductor, the higher the resistance it will offer to the electron flow. So, resistance also depends on temperature. Now, usually, the conductor carrying an electric current is a wire, and it is surrounded by a covering of insulation so that the current can't leak away. The resistance of the insulation itself, obviously, has to be very high indeed. But the longer the wire, the more chance there is of the current leaking away through the insulation. So the lower is the insulation resistance. On the other hand, if you double the thickness of the insulation, the harder it will be for the current to leak away. So the higher the insulation resistance. In this part of the course, we have talked about the magnetic fields produced by current flow, and we have seen how they form the basis for the electromagnet. We saw the left-hand rule for the direction of lines of force round a wire, and we heard about the dart symbols for current direction. Then we talked about electromotive force and about potential difference. And finally, we had a look at the resistance of conductors and at insulation resistance and what they depended on. In the next part, we will discuss the most important law in electricity, Ohm's law. Continuing our study of basic electricity, we come now to Ohm's law, the most important law in electricity. So far we have learned that current is electrons flowing in a conductor. When a certain very large number of electrons flows per second, we say we have a current of 1 ampere, or 1 amp, for short. For reasons we won't go into, this number of electrons is about 6¼ million. We've also heard that the force driving these electrons around a circuit, the electromotive force, is measured in volts. A simple cell provides an EMF of about 2 volts. Now, suppose we connect such a cell to a circuit so that a current of 1 amp flows in it. If we double the EMF by connecting 2 cells together, the current will also double to 2 amps. So current and voltage increase together. But we also know that circuit has resistance to the passage of current. If in a circuit a voltage source of 1 volt pushes a current of 1 amp through a lamp, for example, we say the lamp has a resistance of 1 ohm, after the German scientist George Ohm. We can ignore the very small resistance of the bits of wire, by the way. So in any circuit, we have 3 items: the EMF, or pressure, measured in volts, the current measured in amps, and the resistance measured in ohms. Incidentally, to save writing ohms every time, we use the Greek letter omega. Omega. So now in our circuit with 1 volt, 1 amp, and 1 ohm, if we put 2 lamps in the circuit, what do you think will happen to the resistance? Of course, it will be doubled to 2 ohms. So what will happen to current? The 1 volt EMF will now only be able to manage half an amp. Or again, suppose in the same circuit we want to push 2 amps through. What might we do? Well, we could double the voltage, and that would do it. But instead, we could put in a bulb with only half an ohm resistance. And now the 1 volt EMF can push 2 amps through the circuit. Now, all these things are very simply summed up in Ohm's law, which says that in a circuit, the EMF is equal to the current times the resistance. That is, volts equals amps times ohms. This law abbreviates to V for voltage, E is also used for voltage, equals I for intensity of current times R. V equals I times R. A simple algebra tells us that this is the same way as saying I equals V divided by R, and R equals V divided by I. So in a circuit, if we know any 2 of the factors, we can calculate the third. For example, if we know the voltage is 6 volts and the resistance is 3 ohms, we can use I equals V divided by R to tell us that the current flowing is 2 amps. An easy way to remember these 3 combinations is to remember this helpful triangle. To use it, you cover up what you want to know, voltage say, and you know it is I times R. Or if you want to work out resistance, cover it up, and you're left with V over I. And finally, current is V over R. And always, V must be in volts, I in amps, and R in ohms. Now, volts, amps, and ohms are all right for some circuits, but we may need to talk of millions of volts, say, or tiny fractions of an amp, say a millionth of an amp. Written out in full, 1,000,000 volts is 1 followed by 6 zeros. To save writing 6 zeros, we often write 1,000,000 volts like this, when we say 10 to the 6 volts. Alternatively, we call 1,000,000 volts 1 megavolt, or 1 MV. Similarly, 1,000,000 amps is 10 to the 6 amps, or 1 megamp. And 1,000,000 ohms is 10 to the 6 ohms, or 1 megohm. In the same way, we refer to 1,000 volts by saying 10 cubed volts, or we use the prefix kilo, as in kilovolts, kiloamps, and kiloohms. So that's kilo and mega. When we come to small fractions of these quantities, 1,000th, say, we use the prefix milli, little m. So we have millivolts, milliamps, and milliohms. Or just as we use 10 with a little 3 for thousands, we use 10 to the minus 3 for thousandths. And finally, we often want smaller fractions still, a millionth, say, and that is called micro, and we use another Greek letter, mu, to stand for micro. So now we have microvolts, microamps, and microohms for the 1/1,000,000th part of the unit. And again, just as we had 10 to the 6 for millions, we have 10 to the -6 for millionths. You will need to become very familiar with these names. Now let's go on to the next topic, which is drawing circuits. Here's a very simple circuit. The short and long line symbol stands for a single cell. The longer line is the positive terminal. If it had been a battery of cells, it would have been shown like this, with perhaps the voltage shown as well. This rectangle stands for a resistance. It might be a coil of wire, for example. You will often come across diagrams where a resistor is shown like this. The sign means exactly the same as this one. There will usually be a switch somewhere in the circuit, and it would be shown on the diagram like this for open, and like this for closed. Of course, many circuits are not driven by batteries, so we have the symbol we saw earlier for any other power source. So this diagram represents this circuit: battery, switch, resistor, and back to the power source. So now in this part of the course we have learned Ohm's law and a little about how to draw circuits. Next we will talk about circuits with several resistors in them and about how we deal with such circuits. We must now learn what is meant by series and parallel resistors and how they can be dealt with. We saw this simple circuit before with its single resistor. Now suppose that instead of this one resistor, we have two resistors connected end to end. We would show them like this on a circuit diagram, and we would say that R1 and R2 were connected in series. Any number of resistances can be connected in series, and so can cells or any other circuit component. Suppose these three resistors are 3 ohms, 8 ohms, and 24 ohms. What do you think RT, the total resistance, would be? Most people would say 35 ohms. That's 3 plus 8 plus 24, 35 ohms, and they'd be right. To get the combined resistance of resistors connected in series, you simply add the individual values together. So R1 plus R2 plus R3 equals RT equals 35 ohms. This combined resistance can now be used with Ohm's law to calculate the current in the circuit. 70 divided by 35 equals 2 amps. And this same current of 2 amps flows through each of the resistances. So with series resistances RT equals R1 plus R2 plus R3 and so on. But there's another way of connecting electrical components. It's like this. When the resistors are connected side by side, they are said to be connected in parallel. When connected to a source of power of, say, 20 volts, there will be the same EMF of 20 volts pushing current through each resistance. But it will not be the same current in each of the 3 paths. Where the resistance is lowest, say R1, the current flowing, I1, will be greatest. Where the resistance is greatest, say R3, the least current will flow. The total current flowing, IT, is equal to I1 plus I2 plus I3. Now we know that the greater the cross-sectional area, the lower the resistance. Connecting resistors in parallel is like increasing the cross-sectional area available. There is, as it were, more room for the electrons to get through. So the equivalent resistance RT of 2 resistors in parallel is less than either one alone. And in fact, to calculate RT, we can't just add resistances together as we did with a series circuit. We have to use a formula. The formula is 1 over RT equals 1 over R1 plus 1 over R2 plus 1 over R3. Now suppose the resistors are 3, 8, and 24 ohms as we had before in the series circuit. Then 1 over RT equals 1 over 3 plus 1 over 8 plus 1 over 24. Simple arithmetic now shows us that 1 over RT is equal to 1 over 2. So by inverting RT in the parallel case equals 2 ohms. You can calculate RT in this way for any number of resistances in parallel. For 5 resistances, say, the formula would be 1 over RT equals 1 over R1 plus 1 over R2 plus 1 over R3 plus 1 over R4 plus 1 over R5, and so on. Sometimes circuits are connected partly in series and partly in parallel like this. They are called series parallel or compound circuits and are quite easy to deal with. Take this one. To find RT, we find first the equivalent resistance for the parallel part. That is 1 over 3 plus 1 over 6, which simplifies to 1 over 2. So the resistance of this part of the circuit is 1 over 2 ohms, which we must now remember to invert to 2 ohms. Now we can think of the circuit as a simple series circuit, with 4 ohms and a 2 ohms resistance. So RT equals 6 ohms. Let's look at one more. This time we must deal with the series part first. 1 plus 3 is 4. So the upper branch is equivalent to a single resistance of 4 ohms. Now we can apply the formula to both branches. 1 over RT equals 1 over 4 plus 1 over 12. That equals 3 plus 1 over 12, or 4 over 12, which is 1/3. So RT is 3 ohms. There's one more circuit we want to deal with. In all circuits we've done so far, we've ignored the resistance of the wires connecting the various components of the circuit. This is often quite in order. However, sometimes long cables may be involved, and these may have considerable resistance, causing a voltage drop across them, which has to be taken into account. For example, if a cable is 20 meters long and has a resistance of 1 ohm per meter, then the resistance of the cable will be as much as 20 ohms each way. If a 5 amp current is flowing, we could use the Ohm's law triangle to show that there is a voltage drop of 100 volts in each cable, a total of 200 volts. Suppose we have a circuit where the resistance of each cable is known to be 0.2 of an ohm, and the battery is providing 200 volts to drive a current through a load of 99 6/10 ohms. Can we calculate the voltage drop across the load? Well, the total resistance of the circuit is 99 6/10 plus 0.2 plus 0.2. That is 100 ohms. So what current is flowing? V over RT gives us that, and it is 2 amps. The voltage drop in each cable is given by I times R. That is 2 times 0.2, 0.4 of a volt. So the total voltage drop in both cables together is 0.8 of a volt, which makes the drop across the load 199 2/10 volts. So we can deal with the resistance of the cables if we need to. During this part, we've learned how to calculate the equivalent resistance for resistors connected in series, when RT equals R1 plus R2 plus R3 and so on. We have learned how to calculate the equivalent resistance of resistors in parallel. 1 over RT equals 1 over R1 plus 1 over R2 plus 1 over R3 and so on. And finally, we heard about the resistance of cables. Now we will think about the resistor, and in particular we will be seeing how to tell the resistance of a resistor using the resistor color code. Looking at a circuit board, it is obvious that resistors are important in a circuit. You might think that the best way to show the resistance would be to print it on the resistor, and this is sometimes done. However, some resistors are too small, or they may be positioned with a value hidden. So a color coding system is used instead. Notice the 4 colored bands. First 3 bands from left tell us, if we know the code, that this is a 12,000 ohms resistor. The code works like this. The color band nearest the end tells us the first figure. In this case, it is brown, which stands for 1. The next band is red, which stands for 2. And the third band tells us how many zeros to add. Orange stands for 3. So 3 zeros. 12,000 ohms. The color of the body of the resistor has no meaning in this system and is simply chosen to be different from the colored bands. The color code is on the resistor color code card, and you should use the card until you have done it so often that you'll never get it wrong. Let's try a few more examples, keeping the color code in mind. This resistor is yellow for 4, green for 5, and orange for 3 zeros, 45,000 ohms. Now this one. Violet is for 7, white for 9, and brown for 1 zero, 790 ohms. All right, one more. Gray is for 8, yellow is for 4, black is for no zeros, 84 ohms. Is a tolerance color, which tells us how accurately the color coding gives the resistance value. For example, this resistor is 100 ohms, and the gold band indicates that the tolerance, or accuracy, is plus or minus 5%. In other words, the resistance shown as 100 ohms may be anywhere between 95 ohms and 105 ohms. That is, 100 ohms plus or minus 5%. The tolerance colors shown as the fourth band are brown for plus or minus 1%, red for plus or minus 2%, gold for plus or minus 5%, and silver for plus or minus 10%. If no tolerance band is shown, the accuracy can be taken as plus or minus 20%, which is often accurate enough. Now, what can you make of this resistor? The color bands indicate a 3 for the first figure and a 3 for the second figure. But what is a gold doing as the third band? Well, when gold appears in the third band, it means take 1/10 of the resistance value indicated by the first 2 bands. So this resistor is 33 over 10. That is 3.3 ohms. If the third band is silver, you divide the indicated resistance by 100. In this case, 25 divided by 100. That is 0.25 ohms. So if you have a gold as the third band, take 1/10 of the value indicated by the first and second band. If you have silver as the third band, take 100. Some resistors are called precision resistors, which are printed with 1% tolerance and value in ohms. Some are also manufactured to particularly high standards. They are said to have high stability, and this is shown by a pink band, like this. So the color code on this resistor tells us that it is 64,000 ohms with a tolerance of plus or minus 10%, and it has high stability. So you can now learn a good deal simply from the way a resistor is colored, relying, if necessary, on your resistor color code card.
These are tiny electronic components composed of semiconductor material. This one is called a transistor. It's an amplifier that serves the same purpose as a triode vacuum tube. This one is a crystal rectifier or diode. It does the same job as a rectifier tube. Both of these devices utilize the same basic principles of operation. Since the diode is simple, we're going to use it as an example to show you some fundamental principles that apply to all transistors and diodes. Here's a circuit that will show that the tiny diode really is a rectifier which conducts current in one direction. The bulb is lighted now. If you reverse the voltage, it won't light because virtually no current can flow through the diode in that direction. Let's see how this crystal rectifier is constructed and what gives it this one-way characteristic. This crystal is made of a semiconductor material, silicon in this case. Germanium and other materials can also be used in the same way. Semiconductor simply means that the material may or may not be a good conductor. Since we are interested in the conduction of the crystal, let's review electrical conduction briefly. Here's a simple DC circuit. The current in the wire consists of negatively charged particles moving through the wire toward the positive battery terminal. These negative particles are called electrons. They are always present in the wire, but they move as an electric current only when voltage is applied. Let's look at this section of the crystal closely. It is one crystal, but to make it a rectifier, each half has been chemically treated or doped so that the two halves conduct electricity differently. In one half, the material is called N-type. In the other half, P-type. Remember, this crystal is one piece, not two pieces joined. Let's look at N-type material first. If the semiconductor material were absolutely pure, its atomic structure could furnish no free charged particles such as electrons. With no free particles available to transport electric current, the semiconductor would be a non-conductor or insulator. The chemical treatment introduces a few foreign atoms, each of which contributes one free charged particle to the crystal. In this case, the charges are negative, so the particles are called electrons and the material N-type, N for negative. The free electrons constantly dart about at high speed, much faster than can be shown here. This motion will increase if the crystal is heated. It will slow down when the crystal cools. The rate of motion depends upon the temperature and is usually referred to as thermal agitation. This is important to the behavior of semiconductor material, but we're much more concerned with the reactions of the free electrons when external voltage is applied. Also, the atoms take no part in conducting current, so let's eliminate both the atoms and the thermal agitation. Let's assume that the whole crystal consists of N-type material. If we apply voltage, current flows. Both the crystal and the wires contain free electrons which carry the current through the entire circuit. Now let's examine the other half of the crystal, which is made up of P-type material. The pure semiconductor material has been chemically treated by adding a few atoms of another material to the crystal. One free positive particle has been supplied by each of these added foreign atoms. This material, so treated, is called P-type, P for positive. The free particles are called holes. These holes act just the same as free electrons when used as carriers of electric current, but are positively charged. These holes are also thermally agitated and are responsive to external voltage. If we apply voltage to P-type semiconductor material, current flows conducted through the crystal by the holes. As you see, the positive side repels the holes toward the negative side of the crystal. In the circuit, this direction is opposite to that which electrons would take. Holes and electrons are created in pairs at the positive terminal. The electrons move through the wire and the holes move into the semiconductor. The holes meet electrons from the wire at the negative terminal and they disappear in pairs. We thus have a continuous flow of current in the circuit since electrons are moving in the same direction in both wires. Let's see how the crystal acts as a rectifier. One half is N-type material containing free electrons. The other half is P-type containing free holes. We have a typical PN junction where the two types meet. Diode operation is predicated on the operation of this junction. When we apply voltage to the crystal, the electrons and holes move away from their respective voltage connections toward the junction because like polarities repel each other. The holes are repelled by the applied positive voltage on the P side, and the holes can easily cross the junction into the N-type material. Eventually, each hole meets an electron. When this occurs, the equal charges combine and cancel each other, neutralizing the energy that kept them in motion. Electrically, they simply disappear. Electrons cross the junction into the P-type material in the same manner where they also encounter and combine with holes. The particles disappearing in these combinations are immediately replaced by other electrons and holes entering the crystal. If the voltage is applied to the crystal, negative to N-type and positive to P-type, current flows. This voltage application is known as forward voltage or forward bias. When voltage application is reversed, the holes and electrons are attracted to the terminals and are drawn away from the junction. Charged particles now find it practically impossible to cross the junction, resulting in virtually no current flow. The crystal, in this state, becomes a non-conductor. This application of voltage, positive to N-type and negative to P-type, is called reverse voltage or reverse bias. Thus, the semiconductor crystal with a PN junction conducts current freely with forward bias, but is an effective block to current flow when reverse bias is applied. This ability to pass and block current in a semiconductor crystal utilizing the PN junction is used not only in diodes, but in transistors. Transistors, like diodes, also consist of one semiconductor crystal. If we remove the cover of a transistor, we find that the semiconductor crystal consists of three sections with two p-n junctions between them. The crystal may be doped so the center section is n-type and the two n sections p-type. This is called a PNP transistor. The crystal will function the same if arranged like this. This is called an NPN transistor. The PN junctions in both cases function as rectifiers. The center section must be very thin, perhaps no more than 1/1000th of an inch thick. The N-type semiconductor material again contains free electrons. The P-type, free holes. Let's see how the transistor functions as an amplifier. If we apply reverse bias to the right-hand PN junction, this will attract the electrons and holes away from the junction so that no current flows. This circuit, connecting the right end to the center section, or collector to the base, is called the collector circuit. It is the amplifier's output circuit. Now let's put forward bias on the left-hand junction. That is, between the left side, termed the emitter, and the base. This is the emitter-base junction and is the amplifier's input circuit. This forward bias allows the electrons in the emitter to easily cross this first junction into the base. If the base were thicker, say 1/4 of an inch, the base emitter junction would operate as a forward biased rectifier or diode, with current flowing only in the emitter circuit. No current would flow across the base collector junction due to its reverse bias. In this configuration, many of the electron and hole combinations take place far into the base material. Many of the electrons do not encounter holes at all until quite some distance past the emitter-base junction. Actually, the base material is quite thin, and most of the electrons pass through it without meeting holes at all. Since the collector is negatively biased with a positive charge, the collector terminal further attracts them across the collector junction, and there is now collector current in spite of the reverse bias. There is practically no current through the base to ground because most of the emitter's electrons pass right through the base to the collector. The thin base contains such a small amount of P-type material that relatively few holes are available for combination. A few combinations do take place in the base and emitter, but this base current is so small that we can ignore it. The emitter current consists almost entirely of electrons which cross the junction into the base. These electrons cross the second junction into the collector and proceed on into the wire toward the positive battery terminal. The collector current is wholly composed of electrons from the emitter, and the collector current is determined by the voltage applied across the emitter base junction. The collector current is controlled by the emitter voltage. This collector or output current almost equals the current in the emitter circuit, since it is basically the same current. Obviously, we do not have current gain. However, a transistor is a good voltage amplifier. When we insert a large load in the collector circuit, we get an output voltage many times as large as the emitter or input voltage. This load has no effect on the collector current, since the size of this current is determined only by the voltage applied across the emitter base junction. The same current will flow regardless of the size of the load, as long as the collector has positive bias to attract the electrons driven into it from the emitter. Thus, we can insert a high resistance load in the output and get a large voltage drop across it. While the output current and input current are practically the same, the output voltage is much larger than the input voltage. Since power equals voltage times current, we have more power in the output circuit than in the input circuit. We have power gain or amplification. The transistor is an amplifier as long as the collector has reverse bias to attract the electrons. However, the voltage developed by the load is opposite to the collector bias voltage. Thus, the output voltage must always be smaller than the bias voltage. If the voltage drop were too large, it would be opposite to and would cancel the collector bias voltage, stopping the action of the transistor. The collector battery voltage and resistance of the load will determine the collector current. There would be no amplification since the emitter battery has lost control of the collector current. Let's amplify the audio frequency signal supplied by a microphone. The minute AC voltage output of the microphone is superimposed on the emitter bias voltage. With a loudspeaker as the load and a typical transistor, the output power might be 150 times as large as the input supplied by the microphone. Transistors are much more efficient than vacuum tubes. This transistor radio is compact. It operates for months on flashlight batteries. Transistors have made possible digital computers such as this. These electronic equipments are only a few of the applications made possible through the advancement of solid-state physics in the semiconductor field.
We must now turn our attention to the subject of electric power. We already know that electric current is the movement of electrons through a conductor, and that there is a force, the electromotive force, driving the electrons through the circuit. We shall now be thinking about the work done by that current and the power absorbed in doing that work. But first, what is work? Well, in science, work is done whenever a force causes motion. For example, when the force of the expanding steam in the cylinder drives the steam engine, or when the force of the hammer drives in the nail, or of course, when the electromotive force drives the electrons around the circuit. Now, suppose we have a steam engine being driven slowly. It will be doing a small amount of work. But if it is driven faster, it will be doing more work. it will be working at a higher rate. The rate at which work is done is called power. In an electric circuit, the power, the rate at which work is done, depends on the number of electrons moved and the speed at which they travel. But the number of electrons moved is the current flowing in amps, I. And the speed at which they travel depends on the voltage, V, driving them around. So P, the power absorbed in the circuit, is given by V times I, volts times amps, and is measured in watts, W. This is the power formula. P equals VI. We don't always have to say times I. P equals VI is enough. For example, in this circuit, V equals 100 volts and I equals 2 amps. So the power absorbed, P equals VI, that is 200 watts. Or again, this electric heater is connected to a voltage supply of 250 volts and is passing a current of 4 amps. The power absorbed by the heater is 250 times 4. That is 1,000 watts. 1 kilowatt. It's a 1 kilowatt heater. There are other ways of expressing the power formula, P equals VI. You remember the Ohm's law triangle, from which we can say that V equals IR. So if in the power formula we put V equal to IR, it simplifies to P equals I squared R. Similarly, I equals V over R. And if we put this value for I in the power formula, we get P equals V squared over R. So we have 3 ways of expressing power. P equals VI, P equals I squared R, and P equals V squared over R. These are all very useful formulae and should be learned by heart. Perhaps we should try a few examples. You might want to calculate the power absorbed by a resistor R when the applied voltage is 20 volts and the current flowing is 4 amps. Well, P equals VI, which equals 20 times 4 equals 80 watts. Or again, suppose we have a 50 ohm resistor with 5 volts across it. What power is being absorbed? We know R and V, so we use the formula P equals V squared over R to find P. P equals 25 over 50. That is half a watt. Next, suppose we have a circuit with resistors in parallel. One of them has a resistance of 50 ohms and a 10-volt source is driving the current. Can we find the power being absorbed by the 50 ohm resistor? And the answer is yes, easily. Because P equals V squared over R. That is 10 squared over 50, 2 watts. And finally, consider a circuit with a resistor of 30 ohms, a heater say, and a current of 10 amps. What is the power taken by the heater? Well, P equals I squared R. So P equals 100 times 30, which equals 3,000 watts, 3 kilowatts. And this is called the power rating of the heater. So we've seen how we can use the 3 formulae to find the power rating when 2 other values are known. But also, when the power rating P of an electrical item in a circuit is known, we only need to know one of the other 3 values, V, I, or R, in order to calculate each of the other values. because since P equals VI, then P over V equals I, and P over I equals V. And because P equals I squared R, P over I squared equals R. And we have a formula for I, one for V and one for R, when we know P and one other value. Usually electrical equipment is rated for both voltage and power, as on this soldering iron. It's the same with this drill motor, and with this lamp, which shows 240 volts and 60 watts. 60 watts is the power rating, and it indicates the rate at which the lamp converts electrical energy to light. The other lamp, which is rated at 100 watts, when switched on is much brighter than the one rated at 60 watts. It is converting electrical energy to light at a higher rate. Power rating always indicates the rate at which electrical energy will be converted to some other form of energy. Light in the case of lamps, heat in the case of the soldering iron, and mechanical energy in the case of an electric motor. Resistors also absorb power, and so they too have a power rating in watts. These carbon resistors all have the same resistance, but the rate at which they use up electrical energy differs, so their power ratings also differ. The bigger the resistor, the higher the wattage they absorb. When resistors of higher wattage are needed, wire resistors are used. They usually range from 2 watts up to 100 watts, and special ones of even higher ratings are available for power ratings in excess of 100 watts. So, in electricity, the unit of power is the watt, and it is the rate of converting electrical energy to some other form of energy. In mechanical equipment, such as an automobile, say, we use horsepower to indicate the power rating. Since both the watt and the horsepower are rates of doing work, there's a connection between them. And in fact, 1 horsepower equals 746 watts. Finally, a word of warning. This is a sight you should hope never to see again. An electric conductor smoldering. But it can happen, like this. Most conductors use the power they absorb to make heat, but they are usually electrically insulated. And this insulation also tends to keep in the heat generated, so that unless we are careful, the conductor may get overheated and damaged. For this reason, the currents allowed to pass through electrical equipment are limited, so that the heat generated is also kept within safe limits. Neglect this precaution, and the most disastrous and potentially deadly consequences may follow. And that's all we wish to say in connection with electric power. We saw that work is done whenever a force causes motion. And we saw that power is defined as the rate of doing work. In electrical circuits, power is equal to voltage times current. Volts times amps, and is measured in watts. We saw that electrical equipment, including resistors, have a power rating which indicates the rate at which they will change electrical energy into some other form of energy. And we saw that there is a relation between watts and horsepower. In the next part, we will discuss the subject of alternating current. We've now seen and heard a lot about the flow of current in a circuit. But in everything we've seen, the current has always been flowing around in one direction. Such a current is called direct current, DC. In real life, the direct current causes a steady reading to one side of 0 on the measuring instrument. But current also exists in a different form in which the direction of the current goes first one way and then the other, and of course is called alternating current, AC. Here an alternating current is causing the pointer in the instrument to swing first to one side and then to the other side. But this is a very slow alteration, and the sort of AC we will be dealing with changes direction many times in a second. Power generation and transmission for our homes is AC, and there are excellent reasons for preferring AC to DC. Cities, towns, and villages all over the country need enormous amounts of electrical power. To make this power available cheaply, it is distributed at very high voltages, which are far higher than we can safely make use of in our homes. In other words, before we can safely use the power, we have to reduce the voltage somehow. Now it so happens that electrical devices known as transformers can easily change the voltages of AC, either up or down. Transformers cannot change DC voltages. There are literally hundreds of bits of electrical equipment requiring a lot of different voltages, and again, if we use AC, we can make use of transformers to produce exactly the right voltage for each piece of equipment. Alternating current, like direct current, is measured in amps, but with a difference. Let's see what the difference is. Take 1 amp DC. When 1 amp flows, a known, very large number of electrons passes a point in 1 second. Well, it's the same for AC, except that the electrons flow past the point in one direction, then reverse and flow past in the other direction. Suppose we have a simple circuit in which, using some sort of switch, we can make the current flow either way through the resistor, and we plot on a graph the current flowing at any moment. For a little while, with the switch open, there is no current flowing. Then we switch the current on in the positive direction, and at once we have a positive current flowing in the circuit. We show it above the zero line. Then we quickly reverse the direction of the current, so that we now have a similar negative current flowing, and we show that below the line. Every time the current reverses, the graph moves to the other side of the line. This is a waveform of a simple alternating current. Now in most circuits, in practice, it isn't a sudden instantaneous switch of direction like this. Usually the current builds up one way and then decays down through zero to build up again in the opposite direction, before decaying back again to zero. Gradual build up one way, decay. Build up the other way, decay again, and so on. This produces the sine wave. As well as showing the current flowing, the sine wave also shows how the voltage is varying. Starting at zero and going through the complete series of changes, through zero and back to zero again, we say that a cycle has been completed. The time taken for a cycle is called the period. If in 1 second 4 cycles have been completed, we say the AC has a frequency of 4 cycles per second. In this case, the period, the time taken for 1 cycle, is of course a quarter of a second. And from this we can see a relationship between period and frequency. Period equals 1 over frequency. The 50-cycle AC of the British National Grid has a period of 1/50th of a second. Incidentally, instead of saying cycles per second, we use the name hertz. In the United States, all electricity is generated at 60 hertz. The AC supply in a ship is usually 60 hertz, 60 cycles per second also. So diagrams like this are often used to illustrate alternating currents and voltages, and as we heard, this particular one is called a sine wave. The peak value of the current, one way or the other, is called the amplitude of the wave. Sine waves representing AC can differ in amplitude depending on the peak values of the current. And also they can differ in frequency from short peaky waves to broad shallow ones. And they can differ in another important respect which we need to know about. Here are two waveforms of the same frequency, but with different amplitudes. However, they do pass through zero and come to their peak values at the same time. We say that they are in phase. Now suppose that one waveform is shifted to the right, so that the zero values and peak values no longer occur at the same time. The two AC waveforms are said to be out of phase, and the difference between them is called the phase difference. There's one final thing we must know about AC. Suppose the peak value of this AC is 1 amp. It is only 1 amp at 2 instants during the cycle. So it will not provide as much power as a direct current of 1 amp, which is at 1 amp all the time. Although the peak value of the AC is 1 amp, its effective value is considerably less than 1 amp. In fact, there's a formula for the effective value of the alternating currents or voltages. Its effective value equals 0.707 times peak value. For example, an AC of peak value 10 amps has an effective value of only just over 7 amps. The effective value of an AC is called the root mean square value, or RMS value. So the RMS value equals 0.707 times peak value. When alternating currents of voltage are specified, it's always the RMS value. For example, the household voltage of 240 volts is the RMS value. The peak voltage is in fact nearly 340 volts. And now let's sum up. We know what an alternating current is, and that it is most useful where large amounts of power have to be transmitted, and where voltage changes by transformer are required. We have learned what we mean by period and frequency and the relationship between them. We've become familiar with the sine wave way of showing alternating currents and voltages. And finally, we heard about RMS values. In the next part, we'll be thinking about the important topic of induction, which will lead us straight to the transformer and how it works. We've thought about alternating current, and we will now be seeing how it makes transformers possible. But to do so, we must first think about inductance. First, a simple experiment. Here a coil is connected to an instrument for measuring current. We're going to push a magnet into the coil and watch the needle as we do so. There. There was a kick of current as the magnet went in, and there'll be another in the opposite direction as we pull it out again. There. Whenever the lines of force of the magnet cut across the turns of the coil, an EMF, an electromotive force, is induced in the coil, causing a current first one way and then the other. And this is true whenever the number of lines of force passing through a coil change for whatever reason. Now you'll remember that a current flowing in a conductor always produces a magnetic field. In the case of a straight wire, the lines of force encircle it. If the current increases, the magnetic field strength and the number of lines of force will also increase. If the current decreases, the number of lines of force will decrease. On first switching on, as the current builds up, so does the magnetic field. And on switching off again, the field collapses, taking time to do it. This also happens with a coil. We saw that when a current flows in a coil, it causes a magnetic field about the coil. On switching on, the lines of force take time to build up, and on switching off, they take time to collapse again. The results of these changes in the number of lines of force through the coil is that an additional EMF is induced within the coil itself. This is called an EMF of self-induction, or counter-EMF. An important feature of this EMF is that it will always try to stop the change happening. When you switch on, the induced EMF opposes the buildup of the field, slowing it down. And when you switch off, it tries to keep the field going. This is an example of Lenz's law. In general, Lenz's law says that as current increases in a coil, an EMF is induced which opposes the increase. And when the current decreases, the induced EMF tries to keep it going. This property of a coil to oppose change is called inductance. If a coil has many turns and a core of soft iron or other magnetic material, the induced EMF at switch-off may be very high, much higher than the original voltage. It can be so high that there's a spark across the air gap. The induced voltage is momentarily high enough to overcome the high resistance of the air in its effort to keep the current flowing. Such a coil with its core is called an inductor or choke, and is represented on circuit diagrams like this. If for any reason we want to avoid the inductance effect on a coil, we can double the winding back on itself so that the two induced EMFs cancel out each other. This is now called a non-inductive winding, and is shown on circuit diagrams like this. The unit of measurement for inductance is the Henry, and we often need to speak of a millihenry or a microhenry. And now we'll do another experiment. We'll take two inductors and space them apart in a square iron yoke like this. To the left-hand coil, we will connect a switch and battery, and to the other one, we'll connect a current measuring instrument. We now know that if the current changes in the first coil, as at switch-off, say, there would be a self-induced EMF in the coil opposing the change. But what do you think would happen in the other coil, if anything? Well, watch. A kick of current shows on the instrument. Every time the current changes in the first coil, there is an induced EMF in the second one. This is because the lines of force from the field of the first coil are cutting across the turns of the second one, so that as the field changes, an EMF is induced in the second coil. This is the EMF of mutual induction. It must have struck you that if, instead of switching on and off the current, we supply an alternating voltage to the first coil, so that its field changes continuously, we shall induce an alternating current in the other coil. And this is how a transformer is constructed. We call the first coil the primary coil and the other one the secondary coil. The alternating voltage applied to the primary coil is the input voltage, IP. And the alternating voltage produced in the secondary is output voltage, OP. But before we can understand how this arrangement actually transforms the voltage, we need to know something else about induced currents. Suppose we have 5 turns of wire in the primary coil, and 10 times that, 50 turns in the secondary. And suppose we apply an input EMF of, say, 8 volts AC. The output EMF will be 10 times that, 80 volts AC. and we will have stepped up the voltage, and we have a simple transformer. Let's look at it more carefully. The number of secondary turns divided by the number of primary turns equals 50 over 5 equals 10. But the output voltage divided by the input voltage also equals 10. Using obvious abbreviations, this means that the number of secondary turns divided by the number of primary turns equals output voltage divided by the input voltage. And if we do the simple bit of juggling, we get this formula. Secondary turns divided by primary turns times input voltage equals output voltage. All right, let's try another example. And this time we will use the symbol for a transformer used in circuit diagrams, 2 coils and a core. Let's take an input voltage of 240 volts AC, alternating in a primary of 100 turns. And let's take a secondary of 200 turns. What will the output voltage be? Well, the number of secondary turns divided by the number of primary turns times the input voltage equals the output voltage. So the output voltage is 480 volts AC, and we have again a step-up transformer. But you can also have a step-down transformer. Here's one. Secondary turns over primary turns times the input voltage. This simplifies to 5 times 8, that is 40 volts AC. The voltage has been stepped down from 160 volts AC to 40 volts AC. Transformers are constructed in 2 basic forms. This sort, where the coils are separately mounted on a square yoke. This is called a core type. The other type is the shell type, where the secondary coil is wound on top of the primary. Transformers, in fact, come in all shapes and sizes, but they all have one purpose: to step up or step down AC voltage. They don't produce electric power. They merely use the property of inductance to change the voltage. The next part will deal with another very useful property of electric circuits, which is called capacitance. The last part was about the property of inductance, and we now come to another property of electrical components called capacitance. You'll remember that when we were thinking about inductance, we saw that any change in current in a circuit, and thus in the magnetic field, is opposed by inductance. We shall now be dealing with the property of components which oppose any change in voltage. They try to hold down a rising voltage, and they try to hold up a falling one. This property of opposing voltage change is called capacitance, and the components designed to provide capacitance are called capacitors. As we shall see, they can store an electric charge. Often you may hear them called condensers instead of capacitors. They're the same thing. The principle of a capacitor is very simple. It consists of 2 conducting plates parallel to each other but not touching. They are separated by an insulator, which in this case is the air between them. When they are connected to a source of supply, a battery say, they behave as a very simple capacitor. So let's see what's happening. Here are the 2 plates separated by air. The material between the plates, whatever it is called the dielectric. Now when the switch is made, electrons flow from the negative terminal of the battery onto the plate connected to it, making the plate negatively charged. At the same time, electrons are drawn away from the other plate onto the positive terminal of the battery, leaving the plate positively charged. Eventually, the flows will stop when the potential difference between the plates is the same as the voltage applied by the battery. The capacitor is now said to be charged. If the switch is now broken, the charge remains on the plates and the capacitor is storing an electric charge. When charged like this, the capacitor is rather like an electric cell with a positive and negative terminal, and in fact it will behave like one for a short time. Suppose this charged capacitor is now connected through a switch to a lamp. On closing the switch, current will flow for a short time, lighting the lamp, as the electrons rush round the circuit to the positive plate. The flow stops when the electrons have neutralized the positive charge on the positive plate, so that the potential difference between the plates has disappeared. The capacitor is now said to be discharged. In real life, this is easy to demonstrate. Here is a capacitor connected through a switch to a power source. By closing the switch, we charge the capacitor. When we break the switch, the charge remains in the capacitor, as we can easily show. Watch. Incidentally, notice that the screwdriver used to discharge the capacitor has an insulated handle. It's an essential rule never to discharge a capacitor when it is still connected to a battery or the mains. Now, this capacitor was very simple. It would not be very good at storing a charge. Its capacitance is low. It can be improved in a number of ways because capacitance depends on three factors. First, the area of the plates. The larger the plates, the greater the capacitance, the more charge that would be stored. Next, the distance between the plates affects capacitance. The closer they are together, the greater the capacitance. And finally, the dielectric. Here it's air, but if a better dielectric is used, more charge could be stored. The capacitance would be greater. Typical dielectric materials in addition to air are mica, glass, and waxed paper. So the ability of a capacitor to store charge, its capacitance, depends on the area of the plates, the distance they're apart, and the dielectric between them. There are many types of capacitors and a wide variety of shapes, sizes, and capacitances. But those met with are usually of two types, the paper capacitors and the electrolytic capacitors. Paper capacitors take their name from the material of the dielectric. If we take a capacitor to pieces, we find that it consists of two strips of metal foil with leads attached. These are the plates, with a strip of waxed paper between them to form the dielectric. Further strips of waxed paper inside and outside act as insulation. The whole thing is rolled up into a cartridge and sealed with wax into an outer case. Large paper capacitors are usually sealed into metal containers. When paper capacitors become inconveniently large, electrolytic capacitors are used. Here the dielectric is a thin film of oxide on one plate. The capacitor must be connected with the terminal with the red end or spot to the positive side of a DC supply. As with the paper capacitors, there's a great range of shapes and sizes of electrolytic capacitors. When drawing circuit diagrams, the symbol used for a capacitor is this. And capacitance is measured with a unit called the farad, capital F. But a capacitance of 1 farad is enormous. We are much more likely to come across millionths of a farad, which of course are called microfarads, written like this. So now to sum up what we've seen about capacitance. Capacitors are electrical components of a circuit which can store electric charges by becoming charged. You will come across many capacitors, mostly of two types, paper capacitors and electrolytic capacitors. Here are some examples. In the next part, we shall be looking at the various pieces of electrical equipment which are essential to the subject of electrical engineering. We've been thinking about various properties of electricity and electric circuits, and we're now going to see how, using some of these properties, electrical equipment can be developed and used to good effect. But first, a word or two of revision. You remember that dart notation for direction of current. Current toward you, you see the point of the dart. Current away from you, and you see the flights. We'll need this in a moment to explain this experiment. We have two bar magnets set either side of a small dish of salt water, which is a good conductor. Dipping into the water is a red wire swinging from another wire, which is connected to a battery. To complete the circuit, a blue wire leads from the water to the other battery terminal by way of a switch. When the switch is closed and current flows, look what happens. The red wire swings in the magnetic field. Now let's reverse the magnets to reverse the magnetic field. This time the wire moves the other way. We have just seen one of the most fundamental and useful effects in the whole study of electricity. We had a magnetic field with the wire going through it at right angles. When a current was passed through the wire, it moved to cut across the lines of force. This is called the motor effect and is the basis of all electric motors. We need to be able to predict which way the wire will move. And there is a right-hand rule which tells us. You hold your right hand like this, with the thumb and first two fingers pointing in different directions at right angles to each other. Then you hold your hand so that the first finger points in the direction of the field. F for first and F for field. You line up your second finger with the direction of the current. There's a C in second, and C is for current. Now the direction in which the thumb points gives you the direction of motion. There's an M in thumb, and M is for motion. Remember, this is the motor effect, and it is a right-hand rule. In the experiment, when the current was flowing up the wire and the field was away from us, the wire moved to the right. On the diagram, the field was from right to left, and the current was toward us. So, which way would the wire move? We'll try it with the right-hand rule. First finger field, second finger current, thumb motion. The wire moved up the screen. And now, using the motor effect, let's see if we can make a simple electric motor. We take a rectangular loop of wire and put it in a magnetic field. If we pass a current around the loop in this direction, the far side will move up and the nearest side down. If at the moment when the loop is vertical in the magnetic field, we could reverse the direction of the current, the force that had been pulling the top wire up would change to one pulling it down, and the loop would go on moving. This change of direction of the current can be brought about by means of a ring, split into two halves and connected to the loop, and carbon blocks called brushes, carrying the current to and from the half rings. Now, in this position, the negative brush is in contact with the near side wire, and it is moving up. What when the loop rotates to this position and wants the upper wire to start moving down, the connections change over, and the current in the loop changes direction, keeping the rotation going. Here it is in practice, a DC motor comprising a single loop of wire revolving in a magnetic field. The loop of wire is called the armature, and the arrangement of split rings and brushes is called the commutator. Now let's take our simple motor and connect it to a current measuring instrument instead of to a voltage supply. If we make the armature spin in the field, a voltage is generated and a current flows. What was an electric motor has become a generator of electricity. So in a motor, Current flowing in a magnetic field causes motion of the conductor across the field. In a generator, motion across the field causes current to flow in the conductor. And just as we had a right-hand rule for motors, we have a left-hand rule for generators. As before, the first finger points in the direction of the field. The thumb points in the direction of the motion. And the second finger will point in the direction of the current. Try it in this case, where the far side of the loop is moving upwards. First finger, field, thumb, motion, second finger, direction of current. This way. And that's the end of our look at motors and generators. In the next part, we will look at some miscellaneous electrical equipment. We now come to some miscellaneous items of equipment without which electrical engineering could not function. The first one we look at is the relay. Briefly, a relay is a device for switching on a circuit from a distance, using a low voltage circuit to do it, or of course, switching it off again. It's very simple to understand. The main item in a relay is a coil with a soft iron core mounted on a base. Pivoted near the coil is a small bar without a contact at one end and a spring at the other holding it away from the coil. A second contact is mounted on the base and connected through it to a terminal. Another terminal is connected to the pivoted bar. It works like this. When the distance switch is closed, the current flows in a coil, making it an electromagnet. This attracts the pivoted bar, and the contacts come together, completing the main circuit. When the distance switch is opened, the spring pulls the contacts apart, breaking the circuit. Some relays work the other way round, like this one. The contacts are normally held shut by a spring, and when the current flows in the coil, the contacts are pulled open. Leaving relays now, we come to the principle behind nearly all the meters we use for taking measurements on electrical circuits. A coil of wire is suspended between the poles of a permanent magnet. The coil is connected to the terminals of the instrument through a spindle and balance springs. A pointer is fixed to the spindle and passes over a scale. In use, a known proportion of the current in the circuit is led through the spring to the coil. The coil, like the armature of a motor, rotates against the springs until the rotational force is balanced by them. The amount by which the coil has turned is shown by the pointer on the scale, and this is a measure of the full current in the circuit. This simple principle can be adapted to measure any of the quantities we might need: amps, volts, ohms, and so on. Next on our list of electrical equipment comes the potentiometer, which is used simply to vary the voltage across a load. It consists basically of a resistor with terminals A and B at its ends, and a sliding contact connected with a third terminal, C. The sliding contact can move from end to end of the resistor. In use, the potentiometer is connected like this. Terminals A and B are connected across the voltage source, and terminal C is connected to one side, in this case the negative side, through the load resistance, a lamp, say. So the load and resistor form a parallel pair. If the slider is at the right-hand end of the resistor, there is no voltage across the load. If it's at the left hand, the full source voltage is across the load. The voltage across the load will vary uniformly from full voltage at A to 0 at B, at intermediate points of the slider. Notice that because the load is in parallel with the resistor, the effective resistance of the circuit is reduced. Therefore, by Ohm's law, the total current is increased. If sensible control of voltage is going to be achieved without violent current fluctuations, it can be shown that the load resistance should be much greater than the potentiometer resistance. In practice, a potentiometer often looks like this. The resistor can be a coil of wire bent round into a circle with a slider rotating around it, or it can be a carbon track. Of the three terminals, the center one connects with the slide. There's another use for a potentiometer. It can be used as a dropping resistor. For example, if you have a supply of 20 volts and a lamp, say, designed to operate at 6 volts, you have to lose some volts somewhere in the circuit. You could do this by putting a resistor of just the right size in series with the lamp, so that it uses up 14 of the 20 volts. Or you could do it by using a potentiometer with the slider set to give just the right resistance to drop the voltage by the right amount. Used like this, with only two terminals connected, the potentiometer is called a rheostat, a device which actually controls current flow in a circuit. If the sliding contact is at the A end of the resistor, none of the resistance is in circuit, and the current will be a maximum and the lamp will be damaged. If the contact is at the B end of the resistor, all the resistance is in circuit, and the current will be a minimum and the lamp will not light. In this case, if the current control is to be effective, it can be shown that resistance of the rheostat and the resistance of the load should at least be of similar size. And there we'll end this short review of some pieces of electrical equipment. In the next part, we'll be talking about earth grounds and short circuits. We must now think about the important topic of earth grounds and short circuits. Taking the Earth as a whole, it can be thought of as a large uncharged body with a potential of 0 volts. Anywhere on land is at 0 volts, and for all intents and purposes, the sea is at 0 volts also. If you connect any electrical equipment to the Earth or the sea, it would be said to be grounded, and it will always be at earth potential, that is, at 0 volts. So a ship's hull at sea is grounded. It's at 0 volts. On circuit diagrams, this is how an earth-ground connection is shown. Grounding a circuit is a safety measure. It's like this. Suppose you have some item of electrical equipment in its case. Of course, the leads would be insulated from the case, but the insulation might break down, so that the case would be in contact with the live lead. If now you touched the case, you would get a severe, possibly fatal, shock from the supply. Here it's 500 volts. But if you had taken the precaution of grounding the case, even if the insulation had broken down, the case would stay at ground potential 0 volts, and you wouldn't get a shock. Normally, the ground wire carries no current. It is there merely to provide an easy path for the leakage current if the insulation breaks down. So in the equipment we considered, the leakage current flows into the ground or sea, rather than through anyone touching the live case. But because the earth-ground connection offers a very easy path, a very large current may leak through it, large enough to blow a fuse and cut off the supply. With the fuse blown, there's a break in the circuit, and it is now called an open circuit. So one ground in a circuit may be a safeguard against getting a shock if live metal parts are touched. Two grounds in a circuit are a different matter. A short circuit occurs whenever a component with a potential difference across it is bypassed by the alternative path of low resistance, and it needn't be by two grounds. Such low resistance paths are caused by dampness, insulation breakdown through insulation becoming hard and brittle with age or heat, and by accidental damage. Now let's look at the effect that a ground has in different places in a circuit. Here's a circuit of 3 resistors in series with a 50-volt supply. Let's introduce a ground connection at point A. Can we work out the potential of points A to D with respect to the ground potential of 0 volts? Well, the ground connection doesn't affect the current flowing in the circuit. So Ohm's law tells us that current is V over R. That is 50 over 10, 5 amps. Now point A is grounded, so it is at 0 volts. The voltage across the 5 ohm resistor is given by Ohm's law as I times R, that is 25 volts. So point B is at a potential of 25 volts positive with respect to ground. At point C, the 5 amp current has flowed through a total of 8 ohms of resistance from point A. So the potential at point C is 5 times 8. That is 40 volts positive with respect to ground. And of course at point D, which is connected directly to the positive terminal of the 50 volt supply, the potential is 50 volts positive with respect to ground. In this example, if we had made the ground connection at point D would have been at 0 volts, although connected to the positive side of the supply. The other points would all have been negative with respect to ground, and would in fact have been point C 10 volts negative, point B 25 volts negative, and point A 50 volts negative. Things are a little more complicated if the ground is at some intermediate point. Take this circuit, for example, where point C is connected to ground and will have a potential of 0 volts. The current flowing, V over R, that is 30 over 60, is 1/2 an amp. So the voltage across the 30 ohm resistor is 15 volts. Thus, point D connected to the negative side of the supply is at a potential of 15 volts negative with respect to ground. The voltage across the 20 ohm resistor is 1/2 times 20, 10 volts, and is on the positive side of the ground. And finally at point A, the 1/2 amp current will have flowed from the grounded point through both the 20 ohm and the 10 ohm resistors. So the voltage change across them will be 30 times 1/2, 15 volts. That means that point A will be a potential of 15 volts positive. Notice that from point A to point D, 15 volts positive to 15 volts negative, the voltage change is 30 volts, the voltage of the battery. There are only 2 or 3 more points to be made about grounds. First, suppose you have 2 grounds in a circuit like this. You'll remember that this is a short circuit, and the 10 ohm resistor is simply bypassed. As far as your calculations of current and potential go, this is just as if the 10 ohm resistor wasn't there, and the 2 grounds behave as one. Next, you can use grounds as a return path. In symbols, this circuit would be shown like this. Because the resistors are in series, this is called a series ground return circuit. You can also have parallel ground return circuits, which might look like this. And that is all just now about grounds and equipment is a safety measure to avoid shocks. In the next part, we will be thinking about fuses and how they are used to protect electrical circuits.